Patty Simpson with Simpson Math. In this video, we're going to create a two-way table. So here we have a certain virus infects 1 in every 200 people, or we have a 0.5% prevalence, how often it shows up in the population. A test used to detect the virus has a sensitivity, true positive rate, of 80% and a specificity, a true negative rate, of 95%. Create a two-way table to represent the data. So first, with the two-way table, we know that we have two variables. The first variable here, if it's prevalent in 1 out of every 200 people, that means that some of the population has the disease and some of the population does not. So our first variable is, do they have the disease or not? I'm going to put the answers to that along my first row. So they have the virus or they do not have the virus. And then my total. So as I'm creating my two-way tables, this is the first thing I need to do is figure out what are my two variables. So that's one of the variables. The other variable, well, the test is going to detect whether or not they have the virus. So as a person who goes into the doctor to get a test, I'm going to get one of two results back. I'm either going to get a positive or I'm going to get a negative. So the other variable here is, what is my testing result? Positive or negative? So along this first column, I'm going to put that other variable. I test positive, or I could test negative. And then the total number here. So as I create my two-way table, the first thing I have to determine is the variables in my situation. What variables am I collecting data on? Then I'm going to start to fill in this two-way table. And I'm going to use the information I have. First of all, I know that the virus infects 1 in every 200 people. So how many people have the virus? Well, it depends on my population. So if my population is a population of 200 people, if I have 200 people, then I know 1 of those people has the virus. So I could put 200 in my total, and 1 would have the virus. That means that 199 of those people would not have the virus. But maybe my population is larger than that. Maybe my population is 2,000 people. Well, if 2,000 people are in my population, then 10 people would have the disease, and that would mean 1,990 would not. Notice that all I have to do there, if I add a 0 there, I'm adding a 0 there, and I'm adding a 0 there. Again, if my population is larger, say my population is 20,000 people, then that means that I would expect 100 of those people to have the disease. Again, if I have 20,000, I add a 0 there, I add a 0 there, I add a 0 there. So if there are 20,000 people in my population, then I would expect 100 of them to have the disease and 19,900 of them not to have the disease. Then, the next part of my question says, a test used to detect the virus has a sensitivity, a true positive, of 80%. So in other words, those people who come in and actually have the disease, 80% of them we expect to walk away with a positive test. So on our chart, 100 of them have the disease. We know from the sensitivity then that 80% of those will walk away with a positive test. So since I have 100 of them with the disease, 80 of them will walk away with with a positive. That's the true positive. That's the true positive rate. That means that out of those 100, 20 of them walked away with a negative test. They actually have the disease, but they walk away thinking that they do not have the disease. Then we look at the specificity, and the specificity is the true negative. So the people who walk into the office without the disease, they're tested, they should walk away with a negative test. And 95% of the time in this particular test, they do walk away with a negative test. So of those 19,900 people, we can find 95% of that. So you just do 95% times that 19,900. Or, let me grab a eraser. Let me make it a little bigger here. So remember, if I'm doing percent, I'm going to make it 95 over 100, because that's what percent is, times what? 19,900. I can make these zeros become 1. So now I'm just multiplying 95 times 199. So I know that 18,000, multiply that out, and 18,905 people are going to walk away with a negative test. Those 19,900 that walked in without the disease, 18,905 of them are going to walk away with a negative test. But that means that 995 people, subtract there, 995 people walked away with a positive test. They walked away thinking they had the disease when they didn't. So we had a total of 1,075 positive tests, and we had 18,925 total negative tests. This should add up to be that column. So you can always check yourself, make sure that this adds to that, this adds to that, this adds to that, and then across they should all add up as well. So there is our two-way table for this particular scenario. In the future, we're going to look at using Bayes' theorem to determine the probability that we actually have a disease if we're given a positive test, or the probability that we have the disease if we have a negative test. Math made simple. It's Simpson Math. Thanks for watching.